So the next example we're doing is a bit along the same lines. We're just going to evaluate a limit, but this time we need to employ L'Hopital's rule. So again, the strategy is to kind of call it by a dummy function. So we're going to let f of x equal x squared over 2 to the x minus 1. And so the limit as n goes to infinity of a of n is going to equal the limit as x goes to infinity of f of x. So the limit n to infinity of a sub n equals the limit as x goes to infinity of f of x. And so now I'm going to write f of x explicitly as it was given, or as we defined it, which was x squared over 2 to the x minus 1. And this has the indeterminate form infinity over infinity. So this would go to infinity and this would go to infinity as well. So that allows us the use of L'Hopital's rule. And so when we employ L'Hopital's rule, make sure to give some sort of clue as to what you're doing when you use it. So I usually put an LH over my equal sign. So it's still going to be the limit as x goes to infinity, but we're going to take the derivative of the top and the bottom. So we'll get 2x. The derivative of 2 to the x with respect to x is ln of 2 times 2 to the x, and the 1 becomes 0. But notice as x goes to infinity, we still have infinity over infinity. So our indeterminate form allows us to use L'Hopital again. And so I'm going to take the derivative a second time. So I'm going to get 2 on top, and on the bottom, I have to multiply again by ln of 2. So I'll have ln of 2 quantity squared times 2 to the x. And this time, because the top is constant, the bottom goes to infinity and the whole limit is 0. So that's example 4. Okay, the next thing we're going to do is, I think, pretty fun, the squeeze theorem. The example is challenging, but the idea is kind of cool. So basically what we're saying with squeeze theorem is if we have two, I'm going to make my limit a little bit different just for contrast. If we have two sequences whose limit is L, so we're going to let this dashed blue line be L. We have two series, A sub n and B sub n, and they both converge to L. So that means that there's some sort of epsilon band. Again, epsilon is arbitrarily small, but this is just to give an intuition as to how it is supposed to work. So this is L. This is L plus epsilon, right? So I'm epsilon distance above it, and this is L minus epsilon, I'm epsilon distance below it. So what we're really saying is that maybe we'll let A sub n be green. And so we may have A sub n kind of behaving like this, and eventually it falls into the band, right? So here's our A sub n's. And then we're also going to have, actually, let me think of a better way to do this. I'm going to make the A sub n's monotonic. So what we're going to have here, let's do it this way. Let's let A sub n, maybe it starts out kind of large, but eventually it kind of falls into the band here, right? So maybe it's like a 1 over n or something like that. And then we could also have another sequence, B sub n, and maybe it approaches its limit kind of like that, right? So we have these two sequences that both converge to L, but they're different sequences. And then what the squeeze theorem says is that if you have a third sequence, so maybe we'll call it, oh, what color should you be? How about like a bright red or something? Maybe we have, did that do it? Oh, whatever, okay. So then maybe let's say we have a C sub n, right? This is the sequence in question. And it always stays between A sub n and B sub n. So maybe it's doing something like this. But no matter where you look, past a certain point, of course, right? Because we don't care really, when it comes to taking limits of a sequence, we don't really care what happens at the beginning. We're only interested at the extreme values. So what we're really saying here is that if C sub n is between A sub n and B sub n, right? So I guess A sub n was our top. So I'm writing this a little bit backwards, but it's the same idea. So as long as we can kind of squeeze them between then with A and B having the same limit, then so should C. So again, we don't really care what happens at the beginning. We just want this to happen for some point far enough out, right? So you might say for large enough index n. So we use capital N to be kind of like the starting point. So for example, it could be the case that maybe A sub n was like boop here, and then it was like still here. So it's not really following the inequality until after some certain point n. So, right, so this is n. So we can see that after this index n, so this is like A naught in the beginning, A1, A2, A3, da-da-da-da-da, B1, B2, B3, C1, C2, C3. But after a certain point n, you want to say that it kind of falls in line and behaves according to our inequality. So we're going to use the squeeze theorem now on this one. So this is a little bit of a challenging example. So I'm going to set it up. I might break it up into two parts. We'll see what happens. So what we really want to find So remember, we want to say like at a certain point, capital N, all of it's going to fall in line. All of it's going to behave in the way that we need the inequality to behave. So this is just some large enough. And maybe it's, you know, the 100th term or the millionth term, or maybe it's the 7th term. We don't know. We have to find that out. And we also have to pick out two sequences, AN and BN. So we need to find AN, BN. We need to make sure that CN falls between it for some certain high enough index and beyond. And AN and BN need to have the same limit. This is really important. If they don't have the same limit, how can you possibly squeeze it into the same band? Like you might get a boundary for what the limit could be for C of n, but you're not going to get the exact limit. So what we're going to do here is we are going to let C of n, we're going to let A sub n be equal to -1 over 2 to the n. And we're also going to let B of n equal +1 over 2 to the n. And the thing that we notice is that they both have their limit equal to 0. So this is good. They both have the same limit. We really, really need that. But now the hard part comes in. So we need to show, or we want to show rather, so we want to show that for some large enough n, that A of n is less than or equal to C of n, is less than or equal to B of n for all indices greater than or equal to this elusive, mysterious, air quotes, large enough n. So we got to find that out. So let's just write out what the sequence really is. So we know that A sub n is -1 over 2 to the n. We know that C of n is -1 to the n over n factorial. And we also know that B of n was +1 over 2 to the n. So you might be thinking, like, oh, how am I, like, this is a weird inequality to solve. How do I do that? So I'm going to take a pause here, pick up the next video. I'm going to work through the inequality and we'll show that the limit of C of n is 0 as well.